So since we are done with oxidation and reduction in terms of electrons previously, we are supposed to start with oxidizing and reducing agent in terms of electrons. But before we do, a quick review. Remember, oxidation was loss of electrons, reduction was gain of electrons. If a species loses electrons, it's going through oxidation. If a species, an atom, a molecule, whatever that is gaining electrons, it's going through reduction. Okay, so a
Yeah.
couple of more definitions in terms of electrons, although we have already understood these definitions, but this is just a repetition to make sure that you understand the definition in terms of electrons, because what happens is that the examiner may ask you the definition in terms of electrons or in terms of oxygen atoms or hydrogen atoms, right? So starting with in terms of electrons, oxidizing agent is something that oxidizes something else, definitely the reactant it's reacting with, by taking electrons from it. So oxidizing agent takes electrons from the other reactant. Oxidizing agent itself accepts electron, and therefore they are reduced in a reaction. So I hope you remember we studied previously, and I'm going to use a different color over here. I hope you understand we studied that there is oxidation occurring in this reaction on zinc, and there is a reduction occurring on this reaction in copper. Now,
Yeah.
the one on which oxidation is occurring is the reducing agent, and we specifically mentioned in our last class the one on which reduction is occurring is actually the oxidizing agent. All right. So since we have just defined oxidizing agent, and we said oxidizing agent is oxidizes something else, so this copper 2 ions oxidize these zinc ions. Clearly, zinc is going through oxidation. Actually, this one is losing electron. Zinc loses electron to become zinc positive 2, and the same electrons are actually gained by copper ions, to be converted into copper metal. So yeah, oxidizing agent oxidizes others, but gets itself reduced by gaining the electrons. Make sense?
Yeah.
So if this makes sense, the vice versa, reducing agent is going to be something that reduces others by giving electrons to them. They give away electrons, and therefore they are oxidized in a reaction. So reducing agents get oxidized in a reaction. I think both of these make sense now, right?
Uh, so I think I get confused in those.
Okay, if you get confused in those, here is a quick tip. Now, remember that you need to only remember one of this. The other one is the exact opposite. If we
Mm,
write oxidizes over here, we write reduce over here, take electrons away, give electrons to them, give away electrons, accept electrons, oxidized, reduced. Every word is the opposite of the first one.
yeah.
If you can't remember both of these, no problem. Remember, for anything that undergoes oxidation in a reaction is known as a reducing agent, right? And for anything which undergoes reduction in a reaction is actually an oxidizing agent. So simply writing an oxidizing agent gets reduced in a reaction is good enough of a definition. And
Mm.
that's the
All
same
right.
thing that is written over here. Oxidizing agent are reduced in a reaction,
Yeah.
right? And how is
Mm.
something reduced? Remember the oil rig, right? So what happens in reduction? They gain electron. So oxidizing agent gets reduced by gaining electrons. That's how we connect it.
Mm. All
Right
right.
oil rig, right oxidation, right reduction, right reducing agent, right oxidizing agent. This key is every time going to help you by writing the definition. Oxidizing agent, now go backwards. Oxidizing agent gets reduced in a reaction, which means it gains electrons in a reaction. And that's the exact definition written over here. So you don't have to memorize this definition if you find it difficult. Memorize the key, write the key, go backwards, define it in the same way as done in the book.
All right.
Okay, so
Yeah.
I'm going to clear everything. We're going to move forward with an actual reaction. This is the reaction between copper and silver nitrate. Now, this is usually done in class. This is an easy experiment, and students can even do it with their own hands. Now, as it states, it's a reaction between copper. We have the copper wire, and that copper is the wire over here, as you can see. And we have the reaction with silver nitrate. Now, silver is below copper in the reactivity series, which definitely means silver is less reactive, copper is more reactive. So the reaction is going to occur in such a way that copper is going to displace silver, form its own nitrate, and put silver aside, right? The
Yeah.
best part of this reaction is that copper is a pink brown element, as we can see as the color of this wire. Silver nitrate is a colorless solution. But as soon as you see this diagram, you can clearly tell this solution is not colorless. This solution has a light blue appearance. And this light blue appearance is actually because of this copper nitrate compound, right? Which means the reaction has processed. This is actually the after diagram of the reaction. The before diagram of the reaction should have this wire in a colorless solution. Make sense?
So, what's that thing like from the wire, that gray color? What's that?
Very good question. Do you see this one forming over here in the reaction? Silver? Yeah, and that's
Yeah.
the silver which actually deposited on the wire. Since the wire is initiating the reactivity reaction, so the silver tend to deposit all on the wire in the form of a gray spot. And these are actually delicate crystals.
All right. So, how they will be looking like before the reaction?
The wire in a clean, clearless solution, colorless solution.
No. The silver, how does it look like before the
Okay,
experiment?
I'm gonna
that's dissolved in solution. You'll notice that the surface of the copper that's immersed in silver nitrate is starting to plate silver metal. And at the far end, where the copper color is preserved, that piece of the copper strip is above the silver nitrate.
Now, are you noticing the change in color of the solution? This one has a white
After several
background. You can
minutes,
clearly notice it.
it's clear that copper nitrate has been produced and is released into solution, and the strip of metallic copper now is covered with metallic silver. In this reaction, we took copper metal and we placed it into a solution of silver nitrate. A reaction began immediately, and in the process, copper metal replaced the silver ion. The products of the reaction then were silver metal, which we saw form on the strip, and copper 2 nitrate. Copper 2 nitrate was responsible for making the solution turn a blue color. This equation isn't balanced because we have 2 nitrate ions on the product side and only 1 nitrate ion on the reactant side in silver nitrate. We'll put a 2 in front of the silver nitrate to balance the nitrate ions. In the process of balancing the nitrate ions, we also generated 2 silver ions, and they'll be balanced by putting a 2 in front of the silver metal. And this equation is now balanced.
Before
Yeah.
the steps, right?
Yeah. So, sir, the main point is that this silver, like his places, like this hill. No,
By the
sorry,
copper.
the copper displaces the silver, right?
Right. The
Because
copper
yeah,
displaces the silver. Why? Because copper is on
there
top
is
in the
more.
reactivity series or
Mm-hmm.
is more reactive. Right.
Yeah. Okay, I got it.
Okay, great. So if you get it, I hope you understand the fact that this is a redox reaction. Now, copper, being more reactive, lost electrons. So this is definitely oxidation. Why? It's turning from a metal to positive ion. That usually happens by loss of electrons. So oxidation is loss of electrons. On the other hand, silver is being converted from positive silver ion to silver metal, and this is reduction. Why? Because these are gaining electrons, and gain of electrons is reduction. The same thing is mentioned over here, which make copper a reducing agent, and which definitely makes the silver an oxidizing agent. Remember, oxidizing agent is the one that reduces, reducing agent is the one that oxidizes. As simple as
Yeah.
that. Okay, great.
Yes.
If you understand this, let's move on. Now, separating these half equations give us the idea that since copper is going into copper plus 2 from original state, that means there was a loss of 2 electrons, since this is also shown by this charge. Silver, on the other hand, is just positive charge, gains 1 electron to become silver, but in order to balance the whole equation, since this is losing 2 electrons and this is gaining 1, we put 2 before silver to make sure the whole equation is balanced. So we multiply this whole equation by 2, which means we have 2 silver ions in aqueous solution, gaining 2 electrons and being converted into 2 silver atoms in solid form, which represents why we have written 2 over here and why we have written 2 over here. Sorry, my bad, over here, right?
Mm.
So we tend to balance the equation ourselves. I literally played the last part of the previous video uh, because he was balancing the equation in front of you. And since I'm using the same numbers for balancing of equation, it gives you the idea where the 2 comes from, right?
Yeah.
Now, next up, reactions of metals with water. Now, why do metals react with water? Now, any metal above hydrogen in the reactivity series reacts with water. Let's clarify. We need to really go back a few pages before we go with this one. And I am going to go to the very first page of this chapter to make sure that you understand which elements are above hydrogen. Now, this is where hydrogen is placed, and we have a huge list, almost 2/3 of the elements more reactive than hydrogen. Notice potassium, sodium, lithium, calcium, magnesium, aluminum, carbon, zinc, and iron. All of them are more reactive than hydrogen. Now, to remember all these names is a little bit difficult. However, remembering these as less reactive than hydrogen is somewhat easier. So only copper, silver, and gold are less reactive than hydrogen. Rest all the elements are more reactive than hydrogen. Make sense?
Yeah.
If this does, then the reactions I am about to explain to you are going to be easier for you because you understand which metals are more reactive. So what usually happens is that when metals react with cold water, the metal hydroxide and hydrogen are formed. If the metal reacts with steam, which means the water has been used in its gaseous form, it tends to form a metal oxide and hydrogen. As you move down the reactivity series, the reaction becomes less and less vigorous. Why? Because at the bottom of the reactivity series, we have less reactive elements, and less reactive elements actually do less reactive reactions. With less vigor, of course. So less vigorous, which means the any reactive element on top is going to give you a very reactive, vigorous reaction. Let's take a few examples to make sure that we understand this. Let's go example by example. There are many examples in the book. So one after another, we'll compare elements, which one is more reactive, which one is moderately reactive, which one is less reactive. This would give you an idea. So metals below in the hydrogen, the reactivity series, copper, silver, gold. So you understand why we use copper for water pipes. Copper does not react with either water or steam, so copper can be used for both hot and cold water pipes. That was the main idea why we started off using copper for water pipes, because copper never reacted with them. You know what else can we use for water pipes? We can use gold, we can use silver, but since silver and gold are so expensive, so it's better to use copper. I hope that
Mm,
makes sense.
yeah.
Okay, now reaction of potassium, sodium, or lithium with water. Now we understand if they are putting these three names, that means they are probably the most reactive elements on the list on the reactivity series. Now,
Mm-hmm.
these are very vigorous reactions. Okay, but of course the first one is the most vigorous, and then the less one less violent. They become less violent in the order. This is what happens in an equation. Just replace the m by k, na, or li, which means the equation is pretty simple to follow. Every time the equation is balanced by the exact same numbers, no matter we follow the equation for potassium or for sodium or for lithium, it goes in the exact same way. So cut this m out, write k. That's the equation for potassium. Let's undo this. Let's cut it out and write Na. That's the equation for sodium, and that's how easy it goes. If you remember the sample equation, it should be very easy for you to come up with any element, whichever the one the examiner asks for.
All right.
Okay, so moving next, calcium reacts gently with cold water. The gray granules sink, but are carried back to the surface again as bubbles of hydrogen form around them, and the mixture becomes warm as the heat is produced, which means this is definitely an exothermic reaction, a reaction that produces heat. Okay, so these are the gray granules that we have for calcium, and actually when they produce a gas, and since this is one of the lightest gas on the planet, it tends to take the granule with it up top. So the granules keep going up and down all the time until they are completely consumed by the reaction. So calcium hydroxide is formed, as you can see over here. This isn't very soluble in water. Some of this it dissolves to give a colorless solution. Most of it is left as white insoluble solid. So whether you write aqueous, whether you write solid, both ways you're going to be correct. Aqueous means some of it dissolves in water. Solid means most of it does not dissolve. So actually both ways in IGCSE, they consider it correct. This is actually a way of Edexcel giving you a leniency to go with the reactions that have two possibilities. So either one of them can be considered or treated as correct. Moving on, magnesium with cold water. Now, this one is something that is important. You'd notice that we have two different headings: reaction of magnesium with cold water, and then again we have a reaction of magnesium, but this time with steam. Now, if you start off with cold water, the first line is pretty much self-explanatory. It tells you there is no reaction. If the magnesium is very clean, a very few bubbles of hydrogen will form. The reaction would soon stop. This is because magnesium is coated with insoluble magnesium hydroxide, MgOH twice, that forms and prevents any more water coming into the contact with magnesium. So really, with cold water, we can't have a good reaction of magnesium. So if we really want a good reaction of magnesium with water, we need to use the water in the form of steam, which brings us to the next part. Now, we take some mineral wool that is soaked in water. We have the magnesium ribbon. We keep heating it. We directly don't heat the mineral wool. Even if we heat the magnesium ribbon, some of this water would get heated and would come in contact with this red hot magnesium. And that's how the reaction is going to go with. Now, the magnesium wool, the mineral wool isn't heated directly. Enough heat moves back along the test tube to turn the water into steam. The magnesium burns with a bright white flame in the steam, producing hydrogen, which can be ignited at the end of the delivery tube, which actually ignites in the form of a small pop. You are going to hear good popping sound out of it. This is a really fun experiment for students. So white magnesium oxide is formed, and this time it's different. Now remember, I wrote magnesium hydroxide previously with the reaction of cold water. So this time, definitely the product is different. All right.
Sir, sir, the magnesium ribbon will burn.
Yes, burn.
All
That's
right.
a good point. Now, you must be thinking, how can something burn in the presence of water or steam? Something that is displacing hydrogen to get a part of oxygen in the form of, I shouldn't be using the arrow over here actually, I should be using the arrow over here, right? And we can
Yeah.
use the word burn. Remember, anything when reacts with oxygen gives you the oxide, and we
Yeah,
call
yeah.
this a burning reaction. Actually, the same thing is happening over here. It's just that hydrogen was a part of this oxygen atom, and magnesium displaced it to become this. So yeah, it is burning. And actually, it gives you the same bright white flashy flame. So yeah, burning. That's the best part about chemistry. When we study it in detail, we understand it may is be the water being the substance that is reacting, but at the end of this reaction, we're still forming an oxide. And formation of an oxide with this kind of reaction is actually burning. So yeah, we can use the term.
All right.
And this specific reaction that I was referring to, I'm gonna raise this much. And if I rewrite a couple of things, this one, okay, the specific reaction that I am referring to, this would also be done in lab. Students can do it on their own. They can take a magnesium ribbon and they can directly put it in the flame. Magnesium ribbon burns in the presence of oxygen with the same bright white flame. So if this gives us a bright, flashy white flame, and this reaction also gives us a bright, flashy white flame, and in both the cases we have the same product, so why can't we use the same name? Yes, we can. I hope that explains the reason.
Yeah.
Good.
All right.
Now, as soon as I finish this up and I clear it up, you would notice that we have the reaction of zinc and iron up next. Now, I'm going to take you a couple of pages back. Just a second. If I go a few pages back to where we had this, now imagine we have discussed potassium, sodium, lithium. We have discussed, I really need to change the color, calcium. We have discussed magnesium. But we never discussed aluminum or carbon, and we directly jumped to zinc and iron, right?
Mm-hmm.
So we're
Yeah.
missing two elements out of it. And there is an explanation box on the page we were that explains why there is no uh, description for aluminum. Now, you might wonder why there is no description for aluminum steam. Now, the reactivity of aluminum is supposed to be between that of magnesium and that of zinc. However, aluminum has a very slow reaction with steam. Now, this is because it is covered in very thin but very strong layer of aluminum oxide that it forms with steam. Just like magnesium oxide, magnesium is forming its oxide, aluminum tends to form its own oxide with steam. It only shows its true reactivity if that layer can be penetrated in some way. But actually, this layer is quite thick and is not penetrable by steam so easily. So that's why we tend to not discuss aluminum at this point. We will discuss aluminum in your book, but not at this point. A little ahead
So
in
what
the
about
current chapters.
carbon?
Okay, carbon is different, and we do not discuss carbon in your entire book. Mhm. It is different.
Okay.
Okay. Now, reaction of zinc and iron. Now, if we take a look at zinc or iron, it's the same thing. You'll see we have powdered metal or metal granules. We are heating that. We have mineral wool soaked in water. We are actually having uh, a delivery tube, which is connecting it to a setup of cold water. And we are actually producing gas over water. It goes through the delivery through water, and then the gas bubbles out to be collected over here. Okay, let's go through the reaction and understand why are we doing this. Now, with both zinc and iron, hydrogen comes off really slow. It's slow enough to be collected, neither metal burns. Now, in case of zinc, zinc oxide is formed. This is yellow when it is hot, but it becomes white automatically on cooling. We're talking about the solid. It's yellow in start when it's hot and it becomes white slowly when it's cooled down. Now, in case of iron, the iron becomes a slightly darker gray. A complicated oxide is formed. This oxide is known as tri-iron tetroxide, hence the name tells you three iron and four oxygen atoms. So it also produces hydrogen. Now, in this specific experiment, we're writing water every time as G because water is not water, it's actually steam, hence the symbol G, which explains the key point over here. Now, this method is different from what we have been doing in previously, either with magnesium or with calcium. So why are we doing it? Care has to be taken during this experiment to avoid the suckback of gas. If you stop heating while the delivery tube is still under the surface of water, water is sucked back into the hot tube, which often results in cracking. All right.
Yeah.
So you never stop heating before when the delivery tube is still on the surface of the water. You disconnect the delivery tube, and then you can stop the heating after. Okay. Now, hydrogen is collected over water because hydrogen, and you might want to write this down on your book, is insoluble in water. So it won't dissolve in water.
Oh.
Collecting it over water will not be a problem. Actually, collecting it over water is some kind of an advantage. How? Sometimes powdered metal or granules go through this delivery tube, right, along with the gas, but water stops them going all the way up into the test tube. So we have clean gas in the test tube. We don't have any particles along with it. That's actually a good way of doing it. Make sense?
Yeah.
Remember, the metals below hydrogen in the reactivities, such as copper, silver, or gold, do not react with either water or steam, which actually finishes the the topic of reaction with water or steam. All right.
So, sir, how do they usually ask uh, question in the exam related to this topic?
Okay, that's a really good question. Now, let me go a couple of pages back and let's discuss them one by one. Okay. Now, if you look at these reactions, first thing you need to remember is how the equation is going to go for it. So the first thing they might ask for is a word or a chemical equation with specific conditions. Since the equation is different with cold water and steam, so asking you to write the equation, the balanced chemical equation, along with the state symbols is the first and foremost kind of question. And that's pretty common in past
Sir,
papers.
so I should remember those, right?
You should remember these generic ones because this is going to help you form your actual symbol equations. So that's the first thing you need to do. Okay, moving on.
Yeah.
Now, you'd notice that for the potassium, sodium, or lithium, the equation is different. And we only perform them with cold water. Since the reactions are very violent, we do not even go for an unsafe reaction with steam. In case of calcium, it's different with cold water. We don't even try it with steam. But for magnesium, we do try it with steam and cold water. There is almost no reaction with cold water, but there's definitely a reaction with steam. So there are different ways how we are performing these, and you need to remember each and every single one of them because they're not same in terms of reactivity. So it's not just that you need to understand or be able to write the balanced chemical equations along with the state symbols. You should actually be able to go with the apparatus they have been putting over here. What the apparatus is, how do they go
Yeah.
with the experiment, which imparts the exactly heat, what products apart from the oxide or hydroxide it gives, and what can we do with it, right? So these are the things that you can go for. So they may talk about the apparatus, they may talk about why or how they're going with it, they may talk about a word or a chemical equation, they may talk about the difference in reactivities of both, they may talk about difference in conditions, what cold water or what steam can do with different elements. Make sense? This
Yeah.
actually covers all the kind of questions you have about this in past papers. All
All
right,
right.
good. So this covers